They were co-presenting. They were co-presenting.
Can you hear me, Shelley?
Yep, I can hear you.
Should I share my screen?
Let me get your presentation up here.
I can share my screen if you wanted to. It might be easier.
Oh yeah, if you want to share, go ahead.
Yeah, just let me know when you can see it.
Okay, we can see it.
Okay, thank you. Hi, everyone. Thank you so much for inviting me to speak today. Shelley and the team, thank you so much for organizing this. We really appreciate it, all the efforts, and I'm really excited about all the things I've seen today and some of the instruments. Really great work. So happy to be here. If I'm a bit out of focus, you'll have to forgive me. I had my third baby girl born only a few days ago, so my life is kind of a mess. And I woke up this morning to learn I'm giving this presentation, so please be patient with me. Okay, so today I'm going to talk about ORKID, which is the ORKID Keck instrument development effort, aiming to enable visible wavelength camera for diffraction limited resolution at Keck Observatory. I'm speaking for our team. Our team is quite large at this point. A big shout out from here to Max Miller-Blancher, to John, to Shweet, the entire team at Keck. Really, it's been a real pleasure to work with you. I visited the island multiple times at this point, and I'm super excited about the beginning of installation of ORKID on the mountain. So with that, I'll begin. Let me see why it's not moving on my side. Okay, can everyone see that the slide actually moved?
Yes.
Okay, thank you. So some time ago, around the year of 2017, a team of people from Keck and from NASA sat down together and thought about future of astronomy, and specifically came to a few conclusions that we kind of saw coming down both through the ASTRO 2020 and through different strategic plans of ground observatories, which basically laid out the following. Space telescopes are expensive, are complex, launchers are limited in volume and size, and therefore the sizes of telescopes we'll be able to put in space will be limited. And for other programmatic reasons, would be tough to reach a certain size of interest for us. So this is why we saw one of the recommendation of the decadal coming down to a 6.5 meter space telescope at 2045 as one example. And the second thing we've noticed is the large amount of effort that was put into advancing adaptive optics capability on the ground. And we saw a lot of great work in the talks before me about super smart people trying to understand how to overcome and compensate for the atmosphere. And just kind of looking down at the horizon, we told ourselves, there must be a way in which space and ground are not just following each other, or like, you know, the UV telescope looks there and then the ground telescope examines in more details the JW, but there must be ways in which space and ground can actively collaborate to perform observations that otherwise would not be possible at for different science cases. From that meeting at 2018 were born a series of missions. One of them is ORCAS, the Orbiting Configurable Artificial Star. And this is kind of the parent program for the ORKID instrument that I'll talk about today. So just kind of in a 1 minute, the Orbiting Configurable Artificial Star is a spacecraft carrying two payloads. One of them is a laser beacon, and the second one is a flux calibrator. The laser beacon was designed and is aimed to be used as a reference, what we call artificial guide star that is tunable, both in properties and spectrum, etc. And we'll talk more about that later, maybe not today. And the flux calibrator was designed specifically to address questions of that deal with dark matter and with flux measurements of star or other constant, or basically focusing on very basic properties of astronomical objects and measuring them precisely. And out of that program were born multiple payloads. The first payload was granted to General Atomics, was fully designed and is ready to be built. The second one was funded through the NASA APRA program, that's the flux calibrator. The spacecraft was designed by Blue Canyon Technologies, and the ground effort is being managed in collaboration between Keck and NASA. One of the first questions that were asked by us is, would Keck be able in time to enable near diffraction limited observations in the visible? And we kind of looked at the horizon and we told ourselves that we did not want to kind of fall into a cubicle that says, if somebody fund us, we would be on sky at 20XX, complete the following two letters. And we decided to move with an aggressive program to develop key technology pieces that would demonstrate that this kind of mission could happen. One of them is the ORKID camera. So I'll jump into that. Maybe, excuse me, I'll just go straight to here. So the first thing we've done before starting designing the instrument was to lay down through an analytical calculation what would be the capabilities of such a mission, both in angular resolution if it's used by Keck, and what is the specific field of interest, science field of interest for that type of instrument or mission. And we've learned, of course, that visible science instrumentation, near diffraction limited, at wavelengths that go down to 500 nanometers about, and covering all the way to the gap that we see there for the different missions is a region of interest. But the second thing we notice is that also that the sensitivity gains enormously from the darker sky that we have in that region. And back then it was only a calculation on a piece of paper. But the next question that was asked by the different people who leads the institutions was, can you show us that this is real? Can we do this? So the first thing we needed to do was to develop an instrument that could even observe, and in its ideal case, could actually enable near diffraction limited performance in those wavelengths. And that is what ORKID was built to deliver. The second item of this effort, which I would not talk about today, is focused on actually closing the loop with a flying spacecraft with a beacon at the same time frame. So just so I would give you, all of you, the time frame of when this is happening, we started the effort, I think somewhere around, if I count back, so 90 days ago, we started the clock for 160 days. So within 160 days, we went through design, reviews, fabrication. Then we moved into assembly, integration, testing, and then on sky. So we are now, the box, actually, the ORKID instrument sits on inside the dome, and the spacecraft is basically has a schedule where it shows up anywhere between this November and July. So I'll keep going. This is the night sky, and I guess less about that. But let me just go straight to the instrument. So to the heart of this, what we are doing is we are putting a visible light imager, which we call ORKID, behind the Keck AO2 system. This system will serve as a proof of concept visible light imager with the current Keck AO system, and will be what we call the 0th generation imager for the upcoming Haka upgrade. So in fact, we are not only designing the ORKID instrument, we're also helping in designing the steering mirror on the bench and doing multiple upgrades in real time to advance AO capabilities on the bench at Keck to enable sharper observations. This system leverages a millisecond readout speeds to operate, in this case, in lucky imaging and speckle interferometry modes, enabling diffraction limited science in the visible light regime with the Keck AO system specifically. And this instrument has a range of filters spanning anywhere from 630 to 1,000 nanometers. And that includes a non-redundant mask or an NRM mask and some other interesting optical plays we have in place. And just to kind of give you a feel of where we sit behind the bench. So to the right, you can see the image of the bench. And can you see my pointer when I move it?
Yes.
Yeah.
Great. So this is where ORKID sits, which is basically where ACAM used to sit back at the time. Now it became kind of a double level instrument where ACAM is being fed directly into the system. But if I go back to the optical path, you can see that we have a beam splitter that basically bring us back through a triplet, through our filter wheels, an ADC, so atmospheric dispersion compensator, then a fold mirror, and back to the science mirror. And that allows us to maintain operation at Keck and not intervening with the current way of doing science, but at the same time utilize the visible light that comes towards your towards ACAM in order to do that. Let me take maybe a step back. So why is this interesting for us, and what is the first kind of light science we're going to do? I guess as a step one, I would say that we have two stages to kind of bring ORKID into light. First step is a few engineering nights where we test, calibrate, PSF testing, and so forth, and all those kind of things. But some of our first exciting science targets are solar system targets, including Neptune, Uranus, and Titan. Maybe I should talk a little bit about that. In the decades since Voyager spacecraft flew past Neptune and Uranus, the two planets have changed significantly. Uranus initially devoid of significant cloud feature and has revealed several large clouds features since then, since the North Pole of the planet came to be visible to us. Neptune, on the other hand, has demonstrated a continuous evolution with dark spots and bright clouds frequently appearing and disappearing. So ORKID is aiming to better understand the atmospheric dynamics that cause these features, which is a key step in understanding the detailed atmospheric structure of those planets. And that could only be done through multi-wavelength observation and hence basically multi-pressure level monitoring. Observing in visible band will bring a wealth of additional information to the ground-based NIR observations, since different atmospheric depths are probed at different wavelengths. We specifically plan to observe the two planets in and out of the methane band, so 889 and 643, and the contrast between where the contrast between the clouds and the background is highest at around 889 nanometer, where we probe the troposphere while the deeper layers are probed at 643. So this kind of gives you an idea of what we're starting to chase on the solar system science side. When we talk about binary stars, we are specifically interested in, I guess, maybe a better way of saying this, in observing, well, when observing binary stars with ORKID, we're not only expected to provide improved astrometric precision over NIR measurements because of the smaller PSF, but also the new wavelength range will provide a critical lever arm on the stellar atmospheric models. So if you want to learn more about that, we also share that on our website. And of course, for nearby AGN, where we actually utilize the benefit of using the pyramid wavefront sensor to observe in the near infrared through the center where it's brightest, where we can actually lock on them, and then at the same time conduct observations in the visible.
You're out of time.
I'm out of time. Okay, so I'll stop here. I'll say thank you for everyone. And if anyone wants to have more conversations, our emails and phone are on the screen. Thank you, everyone.
Questions?
Let me check Slack real quick, but I don't see anything in Zoom right now.
For kind of a typical mission configuration, how many different targets can you go to before the satellite starts to run out of fuel?
More targets than you'll have nights to give us. But if you want a more detailed answer, we actually published an entire, it's an AS3 report where we showed you can observe for 300 nights if you needed to, different sets of targets based on the science community needs. If you just type on Google ORCAS plus NASA, it would send you to our page and then go to documents, AS3 report, and you could see the actual on-sky trajectory, fuel consumption, and so forth, the different targets that you'll be able to observe. I think at that point, it's more of a decision of how much time would you like to dedicate to this specific mission or instrument.
I don't see any more questions. Okay, so let's thank Iliad and all the speakers again.
Thank you so much.